So I'll just talk about this work which we implemented recently at University Medical Center Göttingen regarding big data brain MRI. So in recent years, there is availability of largely available data sets, and due to advances in high performance computing facilities, now it is feasible to conduct brain studies on big data. So this work is primarily focused on development of hippocampus profiling for epilepsy subjects. So this basically involves a lot of pre-processing steps and also involves quality control. So when we talk about this big data, so it is the quality control that is challenging, since we have more number of images to deal with, and manual quality control is not feasible, and we need some sort of automatic quality control. So the quality control could start from checking the quality of images before we start pre-processing, and then the quality control comes at the stage of pre-processing, where one important or essential steps involve rigid and affine transformation of the images in a subject space to a template. So that is the step where we focused on developing some kind of machine learning techniques so that we automate the process of quality control of these registrations rather than manually checking. So if I show you, these are, for example, the big data sets currently available, or some of these data sets are currently available openly, so that you can plan your studies accordingly if you want. So the main idea here is to develop a hippocampus profile. So that could be used as a diagnostic tool to compare the hippocampus of patients. It could be epilepsy or Alzheimer's or some other disease. So the basic pre-processing pipeline involves different steps, and for this we have to use different kinds of neuroimaging softwares. So we used a Python-based interface, which is NePipe. So the advantage of NePipe here is that it allows interaction between different neuroimaging software tools such as ANTS, FSL, SPM, affine, and FreeSurfer. So this basically enables you to switch between different tools whenever you feel that certain processing step may be better in using certain software, instead of doing whole process using just one software, right? So I will just briefly discuss about a few pre-processing steps. So once the images are acquired, they have to undergo this reorientation so that they come to the standard reorientation. And then the second step involves cropping, so removing the unwanted portions using the robust FOE tool in FSL. And then the most important step is the Bass field correction. So this could be implemented using two methods, which is N3 in FreeSurfer or N4 in ANTS. So N4 is a bit advanced version of N3, so that that gives you more low field intensity removed version. So here the Bass field is the inhomogeneity field due to the variance of the magnetic field strength along the core. So you can see that in the middle image, and once it is corrected, you can see the low varying intensities are removed. And then once it is Bass corrected, then the subject space images has to be registered to the template. So there are two kinds of registrations here. One is the rigid registration, and the second one is the affine registration. So the second step, P2 to fly to corresponding T1, we can ignore further now. So this is the affine registration, where it involves 12 degrees of freedom. So that means scaling, translation, shear, and rotation. So now the current study focused on these two types, how we check the quality of rigid registration of T1 to MNI and the quality of affine registration of T1 to MNI. So for this, the three cost functions are employed: the normalized correlation coefficient, normalized mutual information, and a correlation ratio. And these were computed locally. So since we used a supervised learning, we need some sort of misaligned images. So the center one is the correctly aligned images. So this is an example shown for rigid registration. So middle one is the correctly aligned image to the template using 6 degrees of freedom, and the top one and bottom one are generated misaligned images, so that supervised learning is possible. So this is how the local costs are computed. So the first equation demonstrates how we computed the cost functions locally by defining a volume of interest. So VS is the size of your volume of interest. We took a volume of interest of 3 by 3 by 3, and ST there represents the stride and how we slide the volume of interest over the images. And M is the moving image, T is the template, and ABC there represent the range of your volume of interest. And cost is your N normalized correlation coefficient or normalized mutual information or correlation ratio. So correlation ratio here is the square root of the equation 4. And W there is some sort of weight because these local cost functions are computed within the brain region. And to avoid the effect of or to avoid the say of these costs around the brain region, because at the brain region, when you define the volume of interest, not all voxels have the intensity values. They may be mostly zero intensities. So we don't want to say that the correlation or mutual information or correlation ratio is high just because it computed only on few voxels. So this weighting factor is introduced there. And the Cn there is the number of local cost computations, which are basically averaged. And these VS and ST, the voxel size and the stride are the free parameters. So for this study, we fixed them to 3 and 3. So for cross-validation and testing, we used a data set from ABIDE, which is Autism Brain Imaging Data Exchange. So we considered 215 T1 weighted images. So out of that, 170 images were used for cross-validation, and the remaining 45 were used for testing. So in the brackets, you can see 87 and 23. They are the number belongs to the patients. So the stratified 5-fold cross-validation was implemented. And in the misaligned case, there are 5 images generated for each correctly aligned image. So you can see that the misaligned images are 5 times higher than the correctly aligned images. And then once we have the cost values computed for each correctly aligned and misaligned images, we implemented several supervised classifiers, starting from linear discriminant analysis, support vector classifier, Gaussian naive-Bayes, and KNN, random forest, and AdaBoost. For KNN, we used a K value of 15. For random forest, we used 100 trees, and for AdaBoost, we fixed 100 stumps. So you can, since the data is misbalanced.
This is your last 2 minutes?
Yeah. So since the data is misbalanced, we used the F1 score. You can see that the F1 scores reaching almost 0.99 for testing. So the cross-validation scores are reported after doing 100 repetitions of stratified k-fold cross-validation. So these are the corresponding ROC graphs obtained on the test set. I can see that they are already almost reaching 0.99 in both rigid and affine case. And since these are developed only on one kind of data, this has to be validated on other cohorts, and also this could be extended for other MRI modalities such as T2 weighted and FLAIR. And to avoid the computation of local cost functions, and a deep learning methods could be developed so that the features are learned automatically for this purpose. So the Python pipeline for this framework is available there in the GitHub. And also, if you want to have a look at the preprint, that is also available in the BioXU server. So thank you.
Thank you,
So
Sudhakar. This looks very